We'll see optimization problems and particularly linear programming. What are optimization problems? Let's start with an example. I'm reading the example that's given in the book. It says a furniture dealer deals in only two items, tables and chairs. He has rupees 50,000 to invest and has a storage space of at most 60 pieces. That is chairs plus tables, maximum 60 pieces can be stored. Now, a table costs rupees 2500 and a chair rupees 500. He estimates that from the sale of one table, he can make a profit of rupees 250 and that from the sale of one chair, a profit of rupees 75. He wants to know how many tables and chairs he should buy from the available money so as to maximize his total profit, assuming that he can sell all the items. Now, as you can see here, we have limited amount to invest. We have limited number of items that can be purchased and sold. The cost of each item is fixed and the estimated profit of each item is also more or less fixed here. The person wants to know what money should he put in these tables and chairs, that is how many number of tables and chairs he should purchase so that his profit is maximum. This type of problem where we somehow seek to optimize the profit or the cost, maybe somewhere we are looking for the minimum cost involved in purchasing something or doing something, and for example here we are trying to get maximum profit out of our investment. So this type of problems is called optimization problem, and we have several techniques involved in optimization problems such as what we are learning. So this is optimization problem, that is we seek to optimize certain parameter. Linear programming is one important type of such class. Non-linear programming is also there, but right now we are looking into linear programming. So let's start with this example only. We say, let's say x is the number of tables that is to be bought and y is the number of chairs. Okay, so we have 50,000 for investment only. That is the cost of one table is 2500, so 2500 into x, and cost of one chair is 500, so 500 into y. It has to be less than, or at the maximum it can be equal to 50,000 because this is our limit on investment. If we buy x number of tables, so x into 2500 will be the cost, and if we buy 500 number of chairs, then 500 into y, this will be the cost of the number of chairs. So this plus this has to be less than equal to 50,000, or let's divide it by 500. So this will be 5x plus y less than equal to, we have divided by 500, so this will be 100. So this is our first constraint, that this plus this can be equal to or less than this. This is the first constraint. Second is the price cannot be a negative number. Similarly, this cannot be negative number. The number of tables and number of chairs cannot be equal to, cannot be less than 0. So these are two other constraints. The next is, we just saw what we want to do. We want to optimize, that is we want to maximize our profit. The profit from one table is 250. So let's say this is z. So 250 into x, if we sell x number of this table, we'll get 250 into x, and 75 on one chair. So 75 into y, this is the profit. Again, try to understand it. The number of tables we buy is x and the number of chairs we buy is y. Total amount that can be invested is 50,000. So if x is the number of tables, then x into its cost is the cost of all tables that we buy. Similarly, y is the number of chairs and 500 is the cost of one chair. So the number of chairs that we have bought, the cost of it is this. Now this plus this is the total cost. Our constraint is that we cannot invest more than 50,000. So this has to be less than or equal to 50,000. So this is the first inequality, this inequality that the constraint poses. This can be resolved to this 5x plus y less than equal to 100. This is the first constraint. X and Y, these are number of tables and chairs, so they cannot be negative. These are the two other constraints. So what will be the profit if we have bought X number of tables and we assume that we sell all the chairs? Then the profit will be this 250 into X, and similarly Y into 75, this will be the profit gained from selling chairs. So the total profit will be this. So what this dealer or what this shopkeeper wants to optimize is this, that is, the person wants to get maximum profit under these conditions. So this is optimization problem, and this is linear. So this comes under the head linear programming. How do we solve it? That is the issue. If we are able to solve this in a way that we get, okay, we should have 10 number of tables and 30 numbers of chairs, that will be very comfortable. That will be so that will give the dealer a very so the dealer would know that if I buy this number of table and this number of chairs, my profit will be maximum. So this is optimization problem. Now we'll see how to solve them. There are several methods. We have graphical method to solve this. We have a method called simplex method to solve this, and there are certain other methods also. This method is used in programming. We use simplex method to write codes so as to optimize our equations. So let's start with graphical method. Let's understand what is the graphical method to solve such optimization problems. So this z equal to, let's say, ax plus by, this is called the objective function. This is called the objective function, and these are the constraints, that this should be less than equal to this should be greater than 0. So I am writing it in the left hand side so that we are able to make the graph in the right hand side. This is 250x plus 75y. Okay, this is our objective function. And what are the constraints? The first constraint is this was 5x plus y less than equal to 100. X is greater than equal to 0 and y is greater than equal to 0. So these are our constraints. Let's see how to solve this using graphical method. Let's make our graph. This is a rough graph. You can use your scale and pencil. So this is y and this is x. How to plot this? We'll use 5x plus y equal to 100 to plot the line. This is less than 100. So what is the meaning of less than? I'll tell you just now. 5x plus y, that is when x is equal to 0, y is equal to 100. Let's say this is 100, 10, 20, 30, 40, 50, because we have to go up to 100, 70, 80, 90 and 100. So this is the point. And then when y is equal to 0, this equal to 0, x will be equal to 20, 100 by 5. So let's say this is 10, this is 20. Let's say this is 30, 40 and again. So our line will be this one, 100 to this point. Okay. So this is our line. Which line? 5x plus y equal to 100. This is the line. So less than equal to 100. This means this area. This inequality means 5x plus y less than equal to 100 means this whole area, complete area, that is to the left of this line, not this one. If this was greater than equal to 100, this area would have been the part. This is less than equal to 100. So this complete area left to this line, complete line, is the graph to the left of this area actually depicts this particular inequality. Now the second is x is greater than equal to 0 and y is greater than equal to 0. That is, we will consider this one only, this line and this line only. See, this line and this line only, here and here. So this part gone. So this is the part. Now let's go to this line. We got this particular triangle from this constraint. Now go back to the question. There was another line that said the number of tables and the number of chairs can at maximum be 60. So that is our next constraint. That is x, number of tables, plus y, number of chairs. It has to be less than or equal to 60. This is our second constraint. So first constraint is this, second constraint is this, and these are two other constraints. So what can we do? X plus y less than or equal to 60. That is x 60 and y 60. So this and let's say this. So a line that will be like this is our x plus y equal to 60. This is a rough figure. So this is the first constraint, this is the second. Again, this is less than or equal to 60. So all below this line, all area below this line is actually depicted by this inequality. So finally, the area that actually covers all these inequalities is this area. See, this one, this area. Let's say these are the points. We say this is O, this is A, B, C. So O, A, B, C, this is the area that actually satisfies all these inequalities. 1, 2, 3, 4. There are 4 inequalities. So the area satisfying all these 4 inequalities is O, A, B, C. This is called the feasible region. That is, any point within this region is the feasible region that satisfies all this point. So is this clear up to now? If this is clear up to now, then we'll go to the next step. So what are these points? This point is 0, 60. So our OABC. So C is 0, 60. What is this point? We'll see. What is O, 0, 0? What is this? This is 20, 0. So we have these 2 points. What is this point? We can have from this one, x plus y equal to 60, and the second line was 5x plus y equal to 100. So if you solve this, you will get this point. So what we will get? 5x plus 5y is 300. We have multiplied throughout by 5. So this minus this is 4y. This is 200. So y is equal to 200 by 4, that is 50. So here y is 50. And what about x? X plus y is 60. So x is equal to 10. So this is 10 and 50. So we have found the fourth point. Clear? So our points are 0, 60, 10, 50, 20, 0 and 0, 0. Now, there are 2 important theorems. First theorem says, I am stating them in very simple way so that you understand. It says that if we have a feasible region that is a convex polygon, then the maxima or minima, that is the optimal solution, lies at the corner only. That is, there are 4 points. The maximum or the minimum for the objective function will be at this point only. That is, when x is this and y is this, or x is this and y is this, or x is this and y is this. This is 0, 0, so that won't be a point. That can be a minimum. Sometimes it can be a minimum. So the first theorem states that at the corners only you will find the optimum point, that is the maximum or minimum. This is theorem 1, important. Second theorem says that we can have there are 2 possibilities. Either we can have a bounded feasible region like this. This is bounded, see. Otherwise, if this was greater than or equal to 0 and this, greater than or equal to 100 and this was also greater or equal to 100, then this and this part would have been the feasible solution, and this was unbounded. This is bounded. If it was instead of less than sign, if this was greater than sign, then above this and above this. So this area, this particular area would have been the feasible solution, and that was unbounded. That is, the limit was not bounded. In that case also, what it says that if the second theorem says that if it is bounded, then we'll have maximum and minimum at the corner points. That you will find a maximum and a minimum, and they'll be at corner points only. So if in this example we have 4 points, 4 corners, you'll have 1 point for maximum and 1 point for minimum. Right now we don't know which is the maximum or the minimum. We'll say it later. But if this is bounded, we'll have maximum and minimum at the corner points. But if it is unbounded like this, then a maximum or minimum, not both, a maximum or minimum may exist. It may not exist. It may exist, but if it exists, it will exist at the corner only. That is, if our case was this one, then this was 1 point, this was 1 point, and this was 1 point. So on these 3 points only, we could have the maximum or the minimum if it existed. How to find whether it exists or not, this we'll see later. But for the time being, you should understand two theorems. First is, at the corners only we have optimum solutions, that is maximum or minimum. Second theorem says, if it is bounded, then maximum and minimum exist, and they exist at the corner points only. So if we have 4 points, one will be our maximum and one will be minimum. And if this was unbounded, then a maximum or minimum may exist, that is, it may or may not exist. But if it exists at the corner points only. Clear? So this is theory. Now we'll see our example. We'll go further in our example. We have 4 points, that is, first is 0 0, then we have 0 60, then we have 10 50, and then finally we have 20 0. These are the 4 corner points. Now I'm rubbing this. Okay, we'll see our result. See, what is the value of z at, this is our O point, this is C point, this is B point, and this is A point. So what is the value at 0? This point. So this will be 0. Then what is the value of z at C? X is 0, so this is 0, and 75 into 60. This is 75 into 60. So what it is? 4500. So the profit that the shopkeeper will get is 4500. What will be the profit at point B? This will be 250 into 10, that is 2500, and 75 into 50, that is 75 into 50 will get 3750. So this will be equal to 6250. See, this value is 6250. That is, the seller will get rupees 6250. What this will be at C? C is 20 0. So 250 into 20, that is 5000. So if the seller sells at this point, he'll get 0 rupees. That is the minimum. See, so if he sells at rupees 0, he'll get 0 profit. If he sells at 0 and 60, that is, not sells at 0 and 60, what I mean to say is, if he buys 0 tables and 60 chairs only, then he'll get a profit of rupees 4500. If he buys 20 tables and 0 chairs, he'll get a profit of rupees 50,000. But if he buys 10 tables and 50 chairs, this is our x and y. That is, if he buys 10 tables and 50 chairs and then sells at this profit, 250 for one table and 75 for one chair, he'll get 6250. And from theorem 1 and theorem 2, we know that we'll get maximum at corner point only. And when we have all our corner points and the maximum is this, then we know that this is the optimum solution. That is, the seller, the businessman should buy 10 tables and 50 chairs and sells. He'll get maximum profit. So this is optimization problem. This is a typical type of optimization problem, that is linear programming. And this is the graphical method to solve this. Okay, I think it's clear to you. We'll see some more examples, some standard forms and examples associated with them, so that everything is very clear before us.